All right, more tools, and this is the one that I promised earlier, that a linear combination of measurable real-valued functions is measurable. So fix a measurable space to start with. Oh, by the way, this is part 2 of Theorem 215. Part 1 is basically is a special case of the composition of measurable functions as measurable result from earlier. So we've covered part 1. Okay, so fix any measurable space X, and suppose f and g are two measurable functions, real valued. So if I just say this, then what I mean is, and actually let me just write it every time. What I mean by measurable is use whatever is the only sigma algebra in the context for X, and use the Borel sigma algebra on R for R. So assume f and g are this kind of measurable functions and take any coefficients, real numbers, alpha, beta, then I'm going to conclude that the linear combination is a measurable function. And again, I mean this kind of measurable. All right, so we're going to actually split it up into 2 steps, which is the same proof basically that's carried out in the textbook. One step looking at scaling and one step looking at addition. So first we'll just claim that alpha f is measurable, and then the second claim is that f plus g is measurable, and that should be enough. The first claim tells you that you can scale, so the same claim can be applied to tell you beta g is measurable, and this claim tells you you can add. So then if you know alpha f and beta g are both measurable, then this claim tells you that their sum is measurable. Okay, so why is alpha f measurable? Well, alpha f is a composition. So it's the composite where you start from x and you use f to go to r, right? And then you go r to r using alpha. Not using, alpha is not a function, it's a real number, using the mapping, let's call it, that takes real numbers to alpha times those real numbers. So this is what is meant by alpha f. It's a so-called pointwise scaling. So it takes it gives you this composite function basically. The f function followed by the scale by alpha function. Okay, so according to our result that composition of measurables is measurable, we would be finished with this claim if we know that each of these is measurable. By assumption, we know f is measurable. That was our assumption up here. Okay, now it's assumed. And what about this? Is this measurable? Well, what kind of sigma algebras are we talking about? The sense in which I know f is measurable requires that I put the Borel sigma algebra on R here. So that must be what I was talking about the whole time when I was saying f is measurable. And the sense in which I want to end up concluding that the composite is measurable also requires that the Borel sigma algebra be here. So there's no doubt. Here we have the sigma algebra A, here we have the sigma algebra Borel R, and here Borel R. Okay, so deciding question, is the mapping x to alpha x a measurable function? Is that a measurable function in the Borel to Borel sense? And this is an example that we looked at earlier in this lecture, where if you have any two metric spaces and a continuous function, then it is measurable in the Borel sigma algebra to Borel sigma algebra sense. Just because the preimage of any open set, and the open sets generate the Borel sigma algebra on here, the preimage of any open set is open. So, so over here, where we are, the preimage of any, the mapping x goes to alpha x, that's continuous, right? Using elementary results way back from Abbott, that this mapping is continuous. If you like, it's the whatever. Yeah, you know how to prove that the functions are continuous. So that's a continuous map. And so any open subset of R, which will be part of a generating collection of sets for the Borel sigma algebra on R, any open subset will have open preimage. Open, therefore Borel. So that's it for that claim, and I'm not doing much writing, so I don't claim that what I've written is a proper proof. It's mostly a diagram and talking. So just in case someone looks at this board and doesn't hear the talking that goes with it, insert words to finish the argument. Okay, and let's look at this claim. F plus G is measurable. This is a little bit more challenging. Well, for a real valued function, to test for measurability, it's sufficient to use that sort of criterion in definition 2.1.1, which is you only need to test basically those functions in what I called fancy R here. Sorry, those sets that are in what I have called fancy R. So because the Borel sigma algebra on the reals is generated by fancy R, measurability for a real valued function comes down to looking at preimages of sets like this. You don't have to consider arbitrary open sets or arbitrary Borel sets. So let C be any real number. Then our goal is to take the preimage of this set, which is an arbitrary element of fancy R, and we want to show that this is Borel. Oh, sorry, not Borel. We want to show that this is an element of script A. So we want to show that this is a measurable subset of X. And script A is the sigma algebra X started with. So that's where we are. So let's break down what this is. It's the set of elements of X, little x, such that f of little x is less than c. Sorry, it's f plus g that I'm looking at here. So it's this, which is, just rearranging this, you can write like this. And this can be written as a union of measurable sets. So let's see how. It's a countable union, so it's going to run over rational numbers R. And I'm going to write it as the intersection of these and these. So this is one of these things that's difficult to come up with this breakdown, but easy to check. So let's just do the check. Let's do the first inclusion from left to right. If you have a little x in here, then f of little x is less than this, right? And then there is a rational number in between, right? These are real numbers. We're looking at real valued functions, f and g. So there's going to be a rational number between these two. So there exists a little r rational between these two. And so then for that little r, you have your little x being in here and in here, right? And then conversely, the other inclusion, right to left, if little x is in here, then there exists a little r so that this inequality is true for your little x and this inequality is true. Then just use transitivity to conclude this inequality, just transitivity of the inequalities. Okay, and what's great about this breakdown is that you've got a countable union, because there are countably many rationals, of these known measurable sets. This one is the preimage under F of this kind of set, and we know those are measurable. And this one is the preimage under G, let's see, of something. So if I rearrange this inequality, this is saying r minus c less than negative gx, so c minus r greater than gx. So like that. And yeah, since f and g are known to be measurable functions, these are measurable sets. So these preimages are both in fancy A. And therefore, so is their intersection. Fancy A is closed under intersection, countable intersection. And so is the countable union of things that are in fancy A. So this is in fancy A. And that's pretty much it. So linear combination of measurable functions is measurable when you're talking about real valued functions, where it makes sense to talk about, point-wise linear combination. So one way to think about it is this is telling you that the real valued measurable functions on x, if you fix x, a measurable space, the real valued measurable functions form a vector space. They're closed under linear combination. So one way to look at why this worked, like why adding two measurable functions ended up being something measurable, is you can think of it as having to do with the fact that addition is kind of a continuous operation. So it's a binary operation. So when I say continuous, I'm talking about functions of two variables. But somehow it is the continuity of addition that allowed us to, that made this work, even though it's not explicitly there. So what I want to do for one of your possible presentation problems for this time is show that if you have any kind of continuous binary operation and you apply that operation point-wise to two measurable functions, then the result is a measurable function. Now the ideas here are pretty useful for that problem, and I think you're ready to give a first try for that problem if you pick that for your presentation problem. But if you don't get it, what I would suggest is also wait till the next lecture. The other parts of this theorem, looking at how we approach those, will probably also give you some helpful ideas for that. And by the way, now that we know that linear combinations of measurable functions are measurable, we have an easy way to, although we probably could have done it explicitly, we have an easy way to say, yeah, here we have described all simple functions on a measurable space X. They are exactly the linear combinations of characteristic functions of measurable subsets of X.